Okay, we are doing our last unit, mini unit on lesson on probabilities. We're going to do compound probabilities. When you think of compound, you think more than one. Okay? Compound means more than one. So we're talking about more than one type of probability. Some of you experienced it yesterday with your making predictions. There were some compound probabilities in that. Flipping two coins, that's more than one. Okay? So we have, with compounds, you have independent events and dependent events. Independent events means that the outcomes do not affect each other. Meaning what I do to one, the second one doesn't matter. An example would be flipping a coin 2 times. Okay? If I flip the coin 1 time, like the first flip, I'm either going to get a heads or a tail. My second flip, same thing. It doesn't matter what happened the first flip. It doesn't matter at all. I'm still going to get either a heads or a tails. Okay, so they don't have any real connection. They don't depend on each other. Dependent means the outcomes do affect one another. So what I do to one depends, what happens that first time affects the probability of the second time. So here's some examples of independent events. Rolling a dice is an example, and tossing coins. What I do to one does not affect the other. Dependent would be if I picked marbles and I didn't replace them. Well, if I start picking marbles, let's say I have a bag full of blue and green marbles. Well, if I pick a marble, the probability of my marble being blue at first is what, 3/5? And then if I keep it, if I hold on to that, I say, well, what's the probability that I'm going to be blue this next time? Well, it's not 3/5. Now I have one that's gone. It would be 2/4, 1/2. Okay, that's a dependent. That's if I don't put something back. And if I draw cards without replacement. That's the key word. I didn't put it back. Okay? So here's to find the probability of compound events contingent that they are independent. That means their results don't affect each other. You do the probability of event A, times the probability of event B. So let's say that we have a bag that contains 3 red cubes and 2 yellow cubes. You draw a cube from the bag and then you put it back. So I still have the same amount of outcomes or possibilities. Then you draw a second cube. Find the probability that both cubes are red. So here's what I'm looking for. Probability of red, then red. So since I put them back, I can just multiply the 2 probabilities. So the probability that I'm red, that I draw a red one, is how many do I have? 3 out of 5. I put it back, so I still have 3 red and 2 blue. So I multiply then by 3/5, which is 9/25. Notice, if I multiply by the same thing, this is really 3 squared over 5 squared, because I have 2 3s, 2 5s. Yep. All right. Suppose we pick a card from a standard deck. We replace. Notice it says replace, so that just means I'm going to go the probability of A times the probability of B. I'm just going to multiply them. Okay? Find the following, that I get a probability of red, then the probability of queen. Well, what's the probability of red?
0.
In a deck?
Half.
Half, right? Half are red, half are black? 1/2. The probability of queen, 4 out of 52, 1/13. Top times top over bottom times bottom. So my probability of drawing a red, then a queen, is 126. Probability of drawing a club, then an ace. Okay? A club, what's a club? 1/13th? Right, but what's the probability? 1/13th, right? It's a fourth of the deck, so let's see, how many? There's 13 out of 52. Do I have this wrong?
Yeah. It's another 1/4.
Oh, duh, yeah, 1/4. Yeah, because 1352 is 1/4, yes. Okay, 1/4. Times the probability of ace, there's 4 aces. Okay, 4 aces, 52 playing cards. What's that turn into? 1/13? They're independent events. That means I'm replacing them. So my probability is equally likely. I still have the same number of outcomes. So it's just going to be top times top over bottom times bottom, 1/52. The probability of black, then a face card. So a black card is a half. Half is black or red, right?
Oh.
Face cards, jack, queen, king, assuming we're not counting aces.
12.
12 out of 52. What's that simplify into? Huh? 3 what? Okay. Independent event because I'm replacing it. So now I just multiply them. 1/2 times 3/13 is 326. Okay. Let's assume there's 30 questions on a test or quiz show. Each question has 4 possibilities, A, B, C, or D. You guess each answer at random, meaning you are using no logic at all. You're just like A, C, D, E, whatever. Okay, you're just doing random guesses. What is the probability that you will get them all right? Kristen, what do you got?
1 in 8.67361738 times 10 to the negative 19th.
Negative 19th. That would, okay, so that's actually not 1/, it's just that. Okay? So, what we would do, the probability that you are right, probability right, is 1/4. Do you agree with that? Probability of getting 1 right is 1/4. Yes? So probability then of getting 30 right, well, you go 1/4 times 1/4 times 1/4 times 1/4 times 1/4. How many times?
30 times.
30 times.
So 4 times 30 would be good.
What do you mean 5?
You did 5 1/4, since there are only 4 answers that you can choose from.
Right,
Yeah, it's 30 times though. 30 questions.
right, 30 questions. Times 1/4, and you would keep going until question 30. And you would do 1/4. Now notice what happens. 1 times 1, that's 1 squared. 1 cubed, 1/4. 4 squared, 4 cubed, 4 to the 4th. Do you agree with that?
Yeah.
So it's actually going to be the probability that they are all right is going to be 1 to the 30th, because I'm going to multiply 1 by itself 30 times, over 4 to the 30th, because I'm going to multiply itself 30 times. 1/, a really big number. In other words, don't just randomly guess. You are going to be that outlier in our data set.
Yeah,
Okay.
what's the chance you actually would get one right?
That's the theoretical chance. Okay, looking at this table, a table shows colors for 20 shirts. A clerk selects 1 shirt from a rack at random, puts a tag on it, keyword replaces it. All right, they're independent. Okay, she's just putting it back, or he just putting it back. So I still have the same outcomes. Find the probability that the first shirt is blue and the second one is red. Okay, because the first shirt is replaced, these are independent. I already talked about that. So probability of blue times the probability of red. That's what we're looking. Well, what's the probability of blue? 6/20. I don't have to add them up. I'd be nice if I can. They told me right away 20 shirts. Okay. 6/20 turns into what, 3/10?
Yeah.
Okay. Probability red. 4/20?
1/5.
1/5. Top times top over bottom times bottom. 3/50. What's the probability that it's orange then black? Now you guys do the next two. All right, so again, these are independent events because I am replacing. So the probability of orange is 7/20. The probability of black is 3/20. Multiply them, 21/400. Okay? What is the probability that they are all going to be blue if we pick 7 shirts? Well, probability of blue is 3/10. I got that from right here. So the probability of blue times the probability of blue 7 times. Okay? 7 times. I'll write 7 times so you know where that's coming from. So remember what I said, if you're multiplying the same number, all I really have to do is 3 to the 7 over, what was the other one, 10? 10 to the 7. And I know that because truly what I'm doing is going 3/10 times 3/10 times 3/10 times 3/10 times 3/10. What's that? 1, 2, 3, 4, 5, 6. Whoops. Okay? All right, next page.
This is super.
Okay, probability of dependent. Dependent again means without replacement. So you want to think about that, without replacement. What you do is you take the probability of the event, normal, and then the probability of the other event after the first one. So 2 girls and 3 boys volunteered to speak at a school assembly. One student is selected at random. You don't put that student back in, right? They can't speak twice. You're assuming they're only speaking once. And another student is selected. I want to know what's the probability that 2 girls are going to be selected. So I know right away the probability that I'm a girl, or that the probability that I'm a girl is 100%. But the probability that I'm going to pick a girl is 2 out of 5. Do you agree with that? 2 girls, 3 boys, 5 total people. The probability that you pick a girl the second time, okay, so this is first, second, well now I only have 1 girl left, right? I already picked a girl. So now I have 1 girl, 3 boys, 4 total people. Okay, so then my probability is you multiply them at the end. 2/5 times 1/4, which is 1/10. Okay? Last one. You select a card at random. The card has the letter M, so we don't care. The letter M is already drawn. Without replacing, you select a second card. Find the probability that the second card is an A after you already selected the M. So an M is gone. I don't care which M. Just an M is gone. I'm holding on to it. So the probability of A, I have 2 A's. How many left? Did it. It's going to stop.